Cauchy was one of the most prominent mathematicians who gave wonderful formulas, proofs, and techniques which shaped the way we solve math today. And one of his works include a marvelous proof for the Basel problem, which he published in the year 1821, which I will be showing you the proof now. In this video, I will be referring to the sum being a special case of the zeta function evaluated at 2. Our goal is to play with the odd terms of the series so we can manipulate the sum by splitting into odds and evens, and from there it's clear how our sum can be linked to the odd reciprocal squares. Now this integral result here is going to be useful and we can prove it. Hint, you can let x equals e to the t and arrive at gamma function. The point is that we want to replace the term in our summation 1 over 2n plus 1 whole squared with this integral by choosing alpha to be 2n. Next, by Fabini's theorem, we are allowed to swap the integral and the summation. And look at that! We have an infinite geometric series inside. And we don't need to worry about x because it is in between 0 and 1 from the integral bounds. We then perform a u-sub and realize that this integral is the same in the regions from 0 to 1 and 1 to infinity. That brings us to the fact that we can replace our 0 to 1 integral with half of the area of the total region from 0 to infinity. Now our goal is to simplify this integral. But how? So we define an integral I of a comma b to help us. Okay, trust me on this, you will definitely understand where we're going with this. Because we notice how a equals minus 1 and b equals 1 is our case. To break down this integral, we use a u substitution, x equals ab times 1 over t. And after some cancellations, we end up nicely with this look of the integral. I am allowed to switch t for x as a dummy variable, so what happens when we add the previous expression for I and the one we have now? Do you see it? Yeah. We'll be able to completely get rid of the natural log term because the x's cancel out in the logarithm and we get a constant out of the integral natural log of ab. And this integral here is pretty easy to evaluate now. And after finding its antiderivative and plugging in the boundary limits, we obtain this. And now for our special case, a equals minus 1 and b equals 1, we see something unusual. Natural log of minus 1. Well, we can consider the principal value of e to the pi I equals minus 1. And using that fact, we get natural log of minus 1 being pi times I. And we know that I squared is minus 1. And there we have it. The integral equals pi squared over 4. And when we finally plug it in, we have pi squared over 6. It does involve some explanation whether we could sub in a equals minus 1, but it can definitely be explained with a bit of complex analysis. And I have to admit, it was really interesting and clever proof. That's it for this video. If you enjoyed it, be sure to like and subscribe and leave your doubts in the comments. Thank you for watching.